Okay, good morning, everyone. Today is the very exciting topic of furans and thiophenes, not because they, in their parent form, make it so much into actual medicines, but rather because of their fact that they are often constituents within bridged or fused heterocycles. So understanding how to make furans is key when we start talking about things like pyrimidinofurans or pyridothiophene. And so if you don't know the basic ways of making these, you're going to be in big trouble. Now, furan is one of the oldest heterocycles, and it was first derivative of furan was isolated in 1780 by Scheele. It's ferulic acid, and furfural is probably one of the cheapest, most sustainable starting materials for any synthesis. And one of the first drugs to use a furan was ranitidine, and this was one of the, I think, the best-selling drug back in 1988. It's no longer sold for reasons that will become clear in just a moment, but anyway, we can go through how it's made. So in the first step, you take furfural, and it is converted to, you have furfural alcohol, and you treat that with a manic condition where you've got dimethylamine and formaldehyde, and something happens. So we talked before about furan being a pi excessive heterocycle. It's pretty reactive. And so in the presence of a nice electrophile, what do you think is going to happen, Aaron? Or Tiffany? Or yeah, Tiffany, what do you say?
I guess it would add into the tube position.
Great. All right, now something weird happens when we treat the manic adduct with this thiol and HCl and heat. Some sort of adduct results. And this one is confusing because we've got several nucleophiles and several electrophiles. So we treat this with acid and heat. What might be the first thing that would happen here, Debbie?
Well, the HCl is gonna protonate the amine and the alcohol, both, maybe. And then SN2, like from the sulfur, that will attack the carbon.
What?
The carbon in which the alcohol, protonated alcohol, is bounded.
You think it's just a straight SN2?
Maybe it can form an adduct with the sulfur, the oxygen, and then maybe, not sure.
We could do something like we saw when we talked about pyrrole, and that is I think what Tim mentioned back in the chlorophyll days when we talked about that, and I guess lecture number 2, wherein these have a strong tendency to make quinomethyde-like species.
Oh yeah, that's true.
And then that will give you the adduct you need.
Phil, would you say a methyl or a methylene at the 2 position is a pretty good indicator of something that could be, I guess, ionized or lost to form that quinomethyde intermediate?
Would I say that a methyl or a methylene? What do you mean by that?
Well, so like with the example from the earlier lecture, and then with this one too, you're forming that orthoquinone intermediate because you have that like CH2 there, and I guess a leaving group.
Yeah.
Would you say that that is like ubiquitous for all heterocycles?
For a lot of them. There's a nice paper from BMS, I don't know, it's about a decade ago, from a medicinal chemist called Marc Saulnier, really talented medicinal chemist. And for example, that orglet was all about how these can be used as these aminothiazoles as linchpin intermediates to do macrocyclizations and all sorts of stitching together. One just has to treat it with tryptic acid and a nucleophile. And the nucleophile can be intramolecular or intermolecular. And the same kind of thing can happen. Just like we saw with the other BMS paper from Jennifer, where they take a trifluoromethyl group that's anionically activated. This one is the same situation. So if you've got a heterocycle and you can draw a resonance form wherein electrons can be moved to kick something out, you can generally invoke this type of reactivity. That's a good question, Tim. Any other questions?
Phil,
Yeah.
why wouldn't the amine leave instead? I mean, the nuclear fugacity is comparable.
Well, in general, an amine is going to be a less favorable leaving group than water.
Okay, so it would be quite selective in this case.
Yes, completely.
Okay.
Okay, great. Any other questions? So how do you make furans? That's a little bit of substitution. How do you make them? Not surprisingly, just like pyrols, it's all about 1,4-dicarbonyl logic. So if you search furan synthesis, you'll find thousands of hits, and we could spend probably 10 hours talking about all the papers of how people make furans, but at the end of the day, they're all pretty much conceptually the same thing. You just look for the 1,4-dicarbonyl and treat it with a little bit of acid and hydrous. You lose the water, and out pops the furan. So what we're going to go through are the strategies and most valuable ways of making furans to help you navigate the 1,000 papers that are out there, so you don't need to memorize all of them. And when you do look for a weird furan synthesis, you can immediately recognize the mechanistic underpinnings and carbon atoms that went into that furan. So probably one of the most useful and maybe oldest furan synthesis is the Weiss-Benari, and it's exemplified with the synthesis of this small furan-based natural product. And it commences with this beta ketoester condensing with this alpha chloroaldehyde. And so we need some help. Usually people use catalytic amounts of pyridine or triethylamine to get these types of reactions to go. It's always very high yielding. And I just need someone to help me with the mechanism to explain the regiochemistry of the product. And perhaps Kelly can start us off with that.
Sure. So you get deprotonation at the beta ketoester, and then you get a tack of that onto the carbonyl carbon of your other reagent.
And then?
And then from here, I think if you draw it like in the enol form, you can kick out water and cyclize to get your product.
Perfect. So in essence, this chlorohydrin was basically a 1,4-dicarbonyl masking, because the oxidation state we need is held there in the form of the water here. Even though this carbon is not at the aldehyde oxidation state, the overall carbon count has the necessary oxidation state you need. It's a theme you see a lot in heterocyclic chemistry, wherein you don't have to be so dogmatic about saying, I need a 1,4-dicarbonyl, for example, or I need a 1,3 or a 1,5 in the case of a pyridine, but rather just say, you know, I need the overall carbon count to contain within it this necessary oxidation state, because it will degenerately go to the aromatic product. There's always that thermodynamic driving force bringing you to the heterocycle. Now, to complete the synthesis, all they need to do is decarboxylate, and they do that by hydrolyzing to the acid and then heating up with copper and quinoline, an ancient way of doing decarboxylations. Okay, let's move on to cycloaddition, which is, I think, the other main way that people look at when they think about making furans. So how would one conceptualize putting together a furan containing 2 ester groups here and here, and 2 methyl groups here and here, using a cycloaddition strategy? Maybe Sung Han can give us an idea.
Can we do the 4+2?
Great. Now, in order to do a 4+2, we need some sort of diene and dienophile. What might be a dienophile?
The alkyne with two ester group.
Awesome. So now we need candidates for dienes. One of the classic ways of doing this is just to take furan itself with the realization that the intermediate you get shown here can do a retro Diels-Alder to give out, let me draw the methyl groups here. You can get a retro Diels-Alder to either give back the starting material or drive off acetylene to give the desired product. And you can do that at a high temperature and remove the gas, and that will drive you to the product. There's another way of doing this. This strategy doesn't always work. There's another way of doing this that uses oxazoles. So for example, this oxazole shown here contains the top half of the furan that we need to access in the cycloaddition. And the product we get results after a loss of benzonitrile.
Do people use oxidiazoles? And are those like easy to make?
Oxidiazoles are pretty easy to make. And I haven't seen anybody use an oxidiazole in a cycloaddition, however, to make a furan, although it's probably known if we search it. Maybe it's a good enough question, Tim, that the TA should probably take a look at that. I haven't seen oxidiazoles, but it seems logical that you could do that to get lose nitrogen. It seems like a good idea. So the TAs will check into that, and we'll get back to you if that is a known reaction. But yeah, it's a good idea. Certainly something you could propose. And oxidiazoles are very easy to make. We will get into how you make those after the midterm in the second half of the class. Okay, so keep that thought, Tim. We'll get back to
Sorry,
you.
I have a question.
Sure, what do you say somehow?
So for the Diels-Alder case, we can lose the ethylene as a driving force, but I think the thiocyanide is not a gas. So what would be the driving force here?
Driving force, just there is a strong cyano triple bond.
Okay, thank you.
Yep. And we will see this again. And Tim, your idea is known. So yeah, we'll send you some nice pure dose for that great idea that you invented that has some precedent. But yes, using that logic, you can invent your own reactions, and often you'll find that they're known. All right, so problem of the day number one is taking what we've learned and seeing if you can put it together to derive syntheses of all of these compounds. So the first one is something reminiscent to what we just talked about, and maybe Simona can help us with what would be a logical disconnection.
Yeah, could you do a 4+2 with TMS acetylene and an oxazole?
That sounds great. Why, what do you think of the reaction with, why do you prefer that over, let's just say, taking furan with the same dienophile, Simona? Why do you think oxazole is better than just taking furan and heating it up?
I don't think you'd have a kinetic driving force driving the reaction forward.
Great, exactly. They're not really very well matched, so you're probably not going to get that first adduct to take place. So yeah, the oxazole is the great way to make this, and you can see here with the dotted lines how that would work, excising benzonitrile.
have a question from the outside.
Question from the outside. What do you say?
Adriana wants to know if you can use just, do you need the phenyl substitution, or can you just use HCN as a gas to lead Cycloaddition?
That I have always seen the phenyl there, just because people don't like to liberate HCN. But we can look into that. I've never seen the corresponding hydrogen one, but you know, almost everything is known. So, but there's a reason people use the phenyl, because the benzonitrile is not toxic, whereas the HCN is a problem. So yeah. But we'll get back to you. Thanks for the question. So let's go to the next one, B. And for this one, luckily Nathan has volunteered to help us with B. Is it going to be a cycloaddition or?
You can start with like 1,3-cyclohexadione, and the other partner could be like an alpha bromide cyclohexanone.
Perfect. Brilliant. Let's go on to the next one. How about C? What are the logical disconnections here? Are we going to do Suzuki City, where we've got multiple different halogens and we try to stitch it together? What do you think is a good strategy here, Carter?
Could we use again a 1,4-dicarbonyl and do Stetter?
Awesome. And how about D? D, what do we think here, Stone? Cycloaddition, ring synthesis, some sort of substitution strategy?
Cycloaddition, I think.
Cycloaddition. And so what would you do there? What would be the order of events?
Take bromoacetylene and the oxazole used in part A.
Like that. Is that the
Yeah.
idea?
Yeah.
Maybe. You know, the issue there is probably, to Simona's point before, I'm not sure if you want to use bromoacetylene if it's going to be a very good dienophile in a reaction like this. So, but I like cycloaddition. The sneaky way people do this is by taking advantage of a really good dienophile, maleic anhydride. And once you have maleic anhydride adduct with furan, you can take this and you can add bromine across the olefin with Br2, followed by base, gives you this, which when heated up, does a retro-Diels-Alder to give you the product. And that's a sneaky way that they make this on large scale, 3-bromofuran. Substitution wouldn't be a good idea because it's going to be a mess. You're not going to be able to really control it. Cycloaddition with a bromoacetylene, while good on paper, is just going to be stymied by the fact that it's not a very good cycloaddition. But maleic anhydride and furan, that's a really good one. And then we know we can brominate that really well, and we know we can eliminate it really well. We can telescope all those steps and then just heat up the product to get out 3-bromofuran. Let's take a look at this example, which introduces us to benzofurans. Benzofurans are not that popular in medicinal chemistry. Usually, if you make a benzofuran, it's going to be en route to something which is much more metabolically stable. And the way to make it more metabolically stable is almost always by making it a pyridobenzofuran, by starting to add nitrogens all around the ring. And we have an entire section of the book that deals with those types of heterocycles if you're interested. But for now, let's just get to this intermediate here. Need some logical ways of deriving what might be the best way of making this type of compound with access to a large family of analogs. So for this, hopefully we can lean on Noor to help us with it.
Yeah, I guess one disconnection I would make is to use a low rock type, so have an
Ah.
alkyne.
That's a good idea.
I guess I'm not sure if I would add the amine substituent before or after.
Yeah, up to you. Good idea. So the R group could either be like an OTBS here, where then you make a library of a million different amines if you're doing medchem, or perhaps your library is only on the arine side and this part always stays constant and you keep the amine in. It really is something that's a judgment call the medicinal chemist would make depending on which part they're trying to get analogs of. But yes, Laroc, Castro, those types of syntheses are almost always, I would say like 80% of the time, are going to be the go-to ways that a medicinal chemist is going to want to make benzofurans, and even the heterocyclic ones too. That's a really good way to put them together. So great.
Phil, I have a question. What's the common metabolite for those benzofurans, and like what do they normally do?
Well, once you epoxidize them, it's game over.
Oh, okay.
Furan says, bye-bye.
Okay.
And this one, you can do this type of thing, and actually the same chemistry happens with indoles. And once you have this is a bad actor. This can be an electrophilic intermediate that starts, or my R. It doesn't matter where your R group is here. This can be attacked by a nucleophile biological one. That's a bad thing. It can be attacked by water, giving a species like this, which can then undergo further oxidation, giving you species like this. And then this obviously hydrolyzes, and now you've got, it could be if the R is equal to H, you've got a salicylaldehyde, which could be a problem. So in general, these things are so messy, people want to avoid them. In the case of thiophenes or benzothiophenes, you often get these types of things. Thiophenes can also, we'll talk about in a moment, give you these types, and the sulfone. Indoles can give you what's known as a formal kynurenine. That, keep that one in mind. This is a formal kynurenine. We'll talk about that, I think, next week. There's actually an enzyme in your body that makes formal kynurenine from indole. There's actually a company that made out pretty well with that enzymatic pathway for combination with checkpoint inhibitors. So yeah, understanding this metabolism is kind of important. And in the case of thiophenes, in some cases, we're not going to cover it, but Plavix is a great example of where this type of oxidation takes place on a thiophene, and it actually forms, this type of oxidation, which then ends up leading to a cleavage to give you this type of thing with a sulfur here. And so Plavix is an example of a drug that was actually approved without fully understanding what the downstream metabolites were. And we actually worked on that project with BMS about a decade ago. It's an interesting little story, but these days, medicinal chemists are far more sophisticated, and the FDA is far more discerning about understanding every possible metabolite. And so in general, what I've observed these days in the industry is that to the extent possible, medicinal chemists want to avoid problematic metabolites. And if there are any, they want to make sure there's one or two, they're totally structurally understood. And that's why you need radiolabeling to find out how they're excreted and what they are. So they're far more discerning, because that's a big issue. If you go all the way to phase 3 and there's a metabolite you haven't explained to the FDA, you are in deep doo-doo, and it could cost the company, I've seen it could cost the company billions of dollars. It happened actually pretty recently. So yeah, good question, Brendan. Sorry for the long answer.
I appreciate it. Thanks a lot.
All right, so let's talk about F. What would be a good, and maybe Brendan, since you volunteered before, you can just help us out with what might be your ruminations on making F. Can we just use 1,4-dicarbonyl?
Definitely not. That doesn't sound like a good idea there.
I don't understand.
Well, because I guess if you draw that back, you still have if you want to bring in that aldehyde and not deal with that later, you're going to have two different options for a 1,4-dicarbonyl.
Oh yeah, that's bad. Okay, thanks.
But I guess if you wanted to not oxidize the aldehyde after, you could, or the alcohol. But in this case, it seems more likely that you would want to just excise the phenylnitrile through the cycloaddition strategy.
So Brennan looks at this and he says, aha, that is my alkyne. And this part here is my oxazole. Is that what you just thought?
Yep. Yeah, that's the idea.
Great. Oxazoles, easy to make. We'll talk about that in the second half of heterocycles. So just for now, trust me, oxazoles are pretty straightforward to make.
Hey Phil, quick question.
Yeah,
Can
what do you say
you
there,
do
Tim?
something like the Weiss-Binari thing here, except instead of an ester, use an aldehyde, or is that? I mean, I could see that you could get regiochemical regioisomers, but could you use an aldehyde instead of an ester?
Generally not. So what you're saying is, why don't we make the ester
or make the ester, then reduce it to the aldehyde?
you want that disconnection, right?
I put one extra carbon between the chlorine and ketone.
Oh, sorry, that was a iPad drawing mistake there. There was supposed to be an extra carbon. Thank you. That's what you want?
Yeah.
I don't see an issue, aside from the fact that what we didn't talk about in Weiss-Binari, that if anyone is interested in, depending on the conditions and the structure of your alpha haloketone, sometimes you can get the wrong regiochemistry, but it is tunable. So as you can imagine, there is a problem where you want the Canova-Nagel to happen, but it's also possible you can get the alpha alkylation. Now, for the purposes of this class, you can assume Weiss-Binari is going to go at the ketone to give you the Canova-Nagel product. And we'll talk about this actually again. Maybe I can recruit you in problem of the day G here, Tim, because it sort of addresses this question. But for a test, putting this suggestion, Tim, I see no problem with it. There's no issue. It's fine. So what do you say there, Tim? Based on that logic, how are we going to make G? Oh, question from the outside?
Actually, a bunch of people asking this.
Okay.
What gives the regioselectivity for the oxazole with the alkyne DWG in this reaction?
So for the 4+2, we just need to look at where does our delta plus and delta minus. So that is clearly the case with that one. And then we need to identify, you know, where, if we look, here's our R group and our aldehyde are here. So our delta minus is here and here. Does that make sense? That's how you can assign the polarity of the oxazole. Great question. Other questions? And that's probably another reason why people use the phenyl, because it accentuates and helps with that polarity assignment. Other questions? Okay. So Tim, what's our answer for the for G?
Yeah, sure. So you can do an alpha haloketone with an beta keto ester. Yeah, with that. And then doing the same mechanism that Kelly mentioned earlier.
Catalytic pyridine or triethylamine should do it for you. Wherein you need this to attack here, followed by a cyclization there. And that will give you the proper regiochemistry. Okay, so the mistake people often make when they think about Weiss-Binari is they say, oh, this is going to attack at the alpha chloro position. And as I said before, there is a paper which studies this phenomenon where you can, by changing conditions, get that to happen. But the canonical 5-spinari involves canovanogel first, followed by cyclization on the chlorine. Okay?
Do you know of any conditions that would favor O-alkylation?
If you wanted O-alkylation specifically, probably a hard deprotonation with something like a potassium with a potassium counterion or a cesium counterion might give you more oxygen alkylation. Okay, great. So now we have radiochemistry problems, and we've got some people in radiochemistry that we haven't heard from. So maybe Camille, who's our resident radiochemist, can help us out with this one.
Can you do 5-spinari again?
Well, I need my other, I don't have a keto ester. So I see. Are you suggesting that, oh, I see. You're saying you're adding a group, aren't you? Is that what you're saying, Camille?
Yeah.
And then decarboxylation.
Mm-hmm.
Now, how do you get the label in?
Yeah, I'm not sure.
Not so easy, huh? And that's why we do radiochemistry, because it forces us not to use the same disconnections over and over again. So what if instead, Camille, we brainstorm on just 1,4-dicarbonyl logic? How about that?
Yeah, looks good. If
we could make this and incubate it with O18 water for a while and acid, we would probably get some enrichment there. It's unfortunately not good enough. And so for their purpose, they used a 1,4-dicarbonyl equivalent, which is this one. Now, when you treat this compound with HCl or H2SO4 dry, it gives you a highly enriched furan with O18 label there. Keep it dry. And this is derived from the corresponding O16 compound just by treating it with O18 water and acid. And then strong dry acid gives you the desired product. You see how that works?
Yes.
Yeah, so for radiochemistry, you're very myopically obsessed with one atom. And the synthesis is based upon that one atom. It's such a weird way of thinking. How about B? Well, if we use the same logic with B, it would require something like that, correct?
Yes.
I've got too many carbons. No one's calling me out on it. There we go. That's better. So for this one, the conceptual equivalent that they use is making this. They take this compound and they treat it for 30 minutes with O18 water to get enrichment here. Then they directly treat that with the coriylate. And when this compound is treated with dry H2SO4, you get the product with our label here. So these strategies are used in order to maximize O18 labeling, because it's really hard to get the oxygen to sit there and stay put How about this last one? Tiffany, Tim, Stone are remaining, Aaron are remaining, Weetree are remaining radiochemists. Anyone want to opine on how you could make this one?
Just methylate B.
Huh.
And butylene methyl halide.
Awesome. Brilliant. All right, let's move on to benzofurans. We talked a little bit about benzofurans, and Noor helped us out with the most popular benzofuran synthesis out there. And here we need 3 different ways of thinking about how to put together a benzofuran. And as we do this exercise, we will basically summarize the 3 most useful conceptual ways of putting these things together. So give me 3 different disconnections. What do you think we could do here? What bonds can we break? In particular, I want you to remember that that carbon is going to be C14 labeled. Aha, so we make it even harder.
Can you break the bond? Well, I would hypothesize to break the bond between the C labeled carbon, so 2 and 3 essentially.
Aha, brilliant. So by looking at that and saying, oh, well, I need to be myopically focused on that 1 carbon atom, it requires us to break the C2,3 bond, and that then leads us back to an intermediate like this. And just treating this with base will give you the product.
I was actually thinking of having the ketone on the other side, so on the labeled carbon, and then you'd have like a doubly benzylic position, which you can alkylate, and then you can get the labeled carbon from something like oxalyl chloride.
Oh, wow. Okay, that's really good. So you want to take that and simply use a strong base deprotonate here and get it to close. Is that right?
Yeah.
You'll need a pretty strong base, but I think it probably would work in this case. Just keep it really dry because that's going to be very hydrolytically labile. It has a good shot of working. You know, it might be best to perhaps use a temporary atom here like a sulfur to help in the formation of that anion, but that's a really hard anion to make. Just keep that in mind. So in practice, it's probably not the first thing I would suggest to someone, just because of the strength of the base needed to deprotonate that and the anhydrous conditions that would be needed, so you don't immediately obliterate that sensitive phenol ester.
Okay.
But it's a good idea. Other suggestions for how we would in general put this together? What if we just go back to your original suggestion, Noor? So we could imagine doing a bromination followed by a Suzuki. And then this might come back from Do you like that? Normally you'd like it, but I've got the radio label there, right?
Yeah.
So not really feeling that one so much. Is there another bond we could break? We have already broken 2, 3. We've broken 1, 2 via the Larock type. Is there another bond we can perhaps break?
Four, 3.
4, 3 could possibly work. And in practice, how we would do that would be in a stepwise way, where first we would disconnect 1, 5. And that would lead us back to an intermediate like this. And then that comes back from something like this. So perhaps this could be BRI or BRCl, where they're differentiated, or even BR might be fine and do the whole thing in one pot, wherein you treat this with palladium or copper, you get the first coupling to go, and then via the enol form of this ketoester, it then cyclizes to give you the 1,5 bond.
How would you do O18 labeled for benzofurans?
That's a really good question. Likely the first thing I would think of in doing that would be to start from a halo compound and use the litany of ways that are out there for doing Ullmann and palladium coupling to install rigidly that phenol, because that can't exchange anymore. Once we've got that phenol there, it's over. O18 is staying put. And then we would do Laroc or whatever we need to do after that. So you could take your phenol, you could halogenate it in the ortho position, and then go on your way with Laroc or whatever you want to functionalize the Friedel-Crafts, for example, whatever you want. There's another way to make these radiolabeled compounds, and I think it's best exemplified using this little consulting corner here. So Nora, what's the problem of using your favorite Laroc disconnection on this compound?
Well, I think one problem would be that you'd have a bromoaryl on the alkyne.
And another problem?
Redo chemistry?
Yeah, brilliant. Great. So we need another way to do this. And we think about breaking that bond there, that's not really good either, because I don't really have anything that can make an enolate very well. So that's not going to be, it doesn't feel very good. I'm running out of ways of doing this. So that's why you need to know 100 ways of making these heterocycles, because often medicinal chemists will ask you these questions, which are really, really frustrating for the consultant, which is to have a polyhalogenated species for which they later on want to do a bunch of Suzuki's and Buchwalds for their modular synthesis. But by doing so, they Laroc block you, in essence. They don't let you make these heterocycles through any kind of palladium coupling because they want to retain the different halogens on these rings for their later on coupling. So you are relegated then to old style condensation chemistry as a result. So for a system like this, the best suggestion would likely be that, where in the intermediate oxime that you make, enolizes, 3,3 happens, and then cyclization to give you your product after loss of ammonia.
I feel. What about iodoesterification? If you have a double bond there, like if you break the bond between the double bond and the aromatic ring, and you like have an olefin, let's say, I don't know if I can explain. Like if you break the bond between the oxygen and the double bond, and you do like iodoesterification. Yeah, and then re-aromatize because you eliminate HI.
For example, that?
Yeah.
Well, again, I'm Laroc blocked. So
and what about some kind of metathesis if you start from a styrene and the enone?
Well, then you're with two olefins that are relatively similar electronically. So we've got this styrene plus that styrene. The reason I would never suggest this to a medicinal chemist is because I cannot, it's not an organ betting level suggestion, as we talked about before. Would you bet your kidney that it's going to give you high yield of the cross product and not just
Sure.
this thing dimerizing or this thing dimerizing. And they only get 10% of their desired olefin at the end. So it's a good idea, but I can't propose it in a consulting session. And therefore, it's not something you should do.
Okay, thank you.
Yeah, great suggestion, though. These are all the kind of things you want to think about. But this one, yes, I'm betting a liver. It's going to work. All right. Thiophenes. Thiophenes are awesome heterocycles because they are found on Mars. So one day, when we're all on Mars, we will have a lot of thiophenes, and you'll remember this class, and it'll help you derivatize them for sustenance, or maybe a flavoring ingredient for your food. Who knows what we'll do over there. So thiophenes, again, 1,4-dicarbonyl logic is the way to go. You have some special features, though, of a thiophene that allow for unique disconnections that are not possible with furans. And that's because of the great reactivity of the sulfur atom, which is a lot different than oxygen. Most notably, sulfur can be an electrophile, allowing for disconnections that would never be possible with an oxygen. So you can use 1,4-dicarbonyl logic. Of course, if you have a 1,4-dicarbonyl and you treat it with some sulfur source, you can get it to cyclize. If you've got a diacetylene like this and you just treat it with HTS, it will turn itself into a thiophene. And again, you can do cycloadditions. However, thiozoles are a lot harder to do cycloaddition than oxazoles, and so I would never recommend this because of temperature involved to make that kind of compound. But I guess if you needed that particular thiophene, that might be something interesting for you to look at. So let's derive what is one of the two most useful ways of making thiophenes. The first one is the Feiselman. The Feiselman comes in many different varieties. And the one we'll discuss right here is this one, which is problem of the day number 3. So if we have a volunteer for some pyridoge, that would be good. Or I will randomly call on someone.
I'll do it.
What do you say there, Alex?
So the sulfur will add into the alkyne. And I guess actually you'll have like double addition, 2 equivalents of sulfur adding in.
Okay, you save some steps, so I'll just draw the adduct directly. Okay, now what? So our
And then
pyridine gets there, and now we do something else.
under basic conditions, you'll have deprotonation, alpha to the sulfur. And that will add into, one of your carbon, the furthest one. And that will get your 5-membered ring, and then a couple of eliminations will get you over to your product.
Perfect. So this is in the right oxidation state here, and all we need to do is lose one of these equivalents, and we get to the nice thiophene product. So there are a lot of Feiselman equivalents, as you can imagine.
Sorry, can I ask a quick question?
Of course.
Why do both sulfurs add in at the same carbon? Is that sterically favorable? Or is it just electronics driving the whole thing?
Well, once you have the first sulfur add in, that deactivates in a strong way the other position. So of the delta positive positions that you've got, there's much more delta positive at the one with the sulfur rather than the one that is beta to it, because you got those electrons pushing in like crazy.
Yeah, that makes sense to me. But why, like, what's the driving force for the second one to go? Just the formation of the thiophene is so favorable?
Well, because you usually, the driving force is that it's still a great Michael acceptor, and you've still got the a thioate there.
Okay.
So thiolates just love Michael acceptors. I mean, to bring it back to pharmaceutical companies in the past 5 years, we've seen an explosion of medicines that have covalent reactive groups based on Michael acceptors. So at the outset, 10 years ago, or maybe a little bit more, you propose an acrylate or an acrylamide in your drug, people would look at you like you've completely lost your mind. But now they're actually pretty hot and they work and they're not toxic and they can be selective. And but yeah, so cysteine and thiolates, active site cysteines, they actually have a voracious appetite for mycoacceptors of all types. So this is a small microcosm of that.
Got it. Okay, thanks.
Feiselman, these are some equivalents of Feiselman. And so to exemplify one of my favorite types of manifestations of Feiselman, let's talk about how you would disconnect that based upon Feiselman logic. Maybe Junchen can help us out here.
Yeah, we can use the same logic as the Feiselman logic, and we can break the break the CS bond. We can break the alpha position of the carbonyl, the CS bond.
Brilliant. Feiselman is always looking for that fragment. Always look for that fragment. How do we make this thing? Anybody know?
Just from the treated with alpha beta unsaturated aldehyde treated with chloride and chlorine and pyridine.
Anybody want to do that?
Yes.
Do you want to do that, Junchen? If I make you go to the lab right now and do that reaction, is that something you want to do?
No.
So are you going to suggest that?
Let's try the carbonyl chlorination maybe. Is that possible? Still not.
Chlorination. Make that compound and treat it with HCl?
Yeah, still not good.
Why is it not good?
I guess you will get a couple mixture of the.
Yep. All right, so we need a good way of making that. And we have a nice introduction here to probably my favorite reagent for heterocyclic chemistry, and that is Vilsmeier. Many years ago, when dinosaurs still roamed the earth, and I would consult at companies before people had ChemDraw and things like that, I brought a suitcase of books with me to each consulting session. And one of those books was just about Vilsmeier. Vilsmeier is one of the most versatile types of reagents that exists out there for forging key functionalities. We're going to see this over and over again through this class. Many heterocycles can be made using Vilsmeier's reagent, and it allows you to just take the corresponding ketone, POCl3, and DMF. What in the world is going on there? Well, that's your first adduct. That's your next adduct. And then your POCl3 will handle your final. Now you can work it up, but you can also do other things with that intermediate too. Stay tuned for that. That's a very, very nice way of turning your ketone into a perfect heterocyclic precursor. You can condense a lot of different reagents into a species like this. Vilsmeier is probably one of medicinal chemists, one of their most useful condensation reagents out there. Question from the outside.
Someone asked if there are friendly alternatives to H2S and or dicarbonyls.
Friendly alternatives to H2S, you can use, I believe, thiourea. I believe that works as well. That's often a nice reagent alternative. Yeah, good question. All right, let's get to now our case studies in thiophene synthesis. So putting it all together, everything you've learned so far in furans and thiophenes, we should be able to put together a coherent analysis of, oh, before we get to that, we don't want to skip Zyprexa, olanzapine. Probably you know someone, or maybe someone even here today has taken it. It's useful antidepressant, useful psychoactive compound made by Lilly. And so we need to identify a good disconnection within here. We've got 3 different rings. We will talk about azapines in a separate class in the second half of the class, but we need a good way to disconnect this into something that might make sense based on what we've learned. So yeah, what do you say, Alex?
You have your like hidden cyano group there in the bottom of ring B. So I guess.
Oh, a hidden cyano group. You think there's a hidden cyano group here? And any other hidden cyano groups, perhaps?
Once you disconnect, so like if you think about disconnecting the nitrogen between A and B on the top half of the ring, then you'll also have like the same motif there. Yeah.
That is really nice. So if we disconnect into those 2 fragments, it's going to require these 2 building blocks. So the order of events to put these together would first be to do your SNAR here, and then reduce this nitro, and then the corresponding amidine that results, the one you get here, can be exchanged with the pyrazine, pyrazine, just by heating it up at about 150 degrees, 120 degrees, sorry, and that will lose ammonia to give you your desired product. So now we have to think about a way to make that. And luckily, you've already told us how we can put together this carbon, because you identified that there is a nitrile hiding. So how do we put that together? What are the ways we can think about? Maybe we can derive another reaction, another popular one to make thiophenes. If we bring it back to a nitrile and just cut it based on first principles, it leads us to what?
A melanonitrile.
Aha. Yes. Let's draw the melanonitrile. And that thing comes from where?
Aldehyde, sulfur, and just melanonitrile.
Okay, so what we're going to do is we're going to take melanonitrile, like Simona says, we're going to condense it, we're going to do our Canova-Nagel, and then in the same pot with base, we're going to add sulfur, just sulfur 8. And as I mentioned before, sulfur is unlike oxygen, that it can be a great electrophile. So that anion that is vanilously activated, namely that one, that's a superacidic position, will attack S8, leading you to this compound, which will spontaneously cyclize to give you that. And you folks have derived one of my favorite thiophene syntheses, known as Gewald. Phenomenal. Questions? Great. Let's make sure we're not skipping anything. Okay, that gets us down now to the case studies. Problem of the day, number 5. So how do we put these things together? So let's see, who have we not heard from today? Maybe, I'm not sure if we called on Daniel already, but maybe Daniel can help us with this one.
All right. I suppose you couldn't do the 1,4-dicarbonyl condensation.
Almost never fails, right?
Yeah.
Fantastic. Is there another way we could do this to make sure? What if, you know, it could be the medicinal chemist says, hey, I don't want to deal with sulfur. I don't want to have any smelly compounds. I don't want to have that aldehyde. Is there another way we could make this? What if we had to insert a group? What if we need to insert a group to make everything easy?
The Feispinari could maybe, yeah, then just go through the decarboxylation and
And you know how to make this, right?
yeah, with the Vilsmeyer.
Yep. Now for the Vilsmeyer, for that mechanism to work, does my ketone go here? Or does my ketone go here?
I think it was the first position.
Brilliant. Awesome job. So we take a simple ketone, we treat it with Vilsmeyer, and we get out this adduct, which then can go and Feiselman its way to victory in a nice medicine. Fantastic. How about problem of the day B? This one is probably signaling for some sort of immediate disconnection in order to simplify our life. And so what would that disconnection look like?
Still me?
Yeah, go ahead. Keep going, Daniel. Yeah.
Oh,
great. As a medicinal chemist, what bond do you think you'd want to break first? Just get rid of something.
maybe the 4 and 6.
Lovely. And now what can we do?
The
Remember this one, Daniel? What is that your signaling element for?
Oh, the Feiselman.
Yes. Every time
Yeah.
you see that, it's screaming out Feiselman. That means this compound is needed. This can be O-triflate, and then we can do Suzuki coupling to put in that biphenyl. And this just comes back from that with dry HCl or POCl3 or oxyl chloride, whatever. And then that can come back to the corresponding ketone. Great. How about C?
Daniel's
going to be a pure Doge trillionaire by the end of the class.
My knee-jerk reaction would be the double 1,4-carbonyl condensation, but that would get you selectivity issues with the different isomers that could be formed. So maybe you could just do one with the.
Love it.
Yeah.
Perfect. All right. How about you know, I mean, Daniel is going to be crowned sort of King Thiophene if it keeps going this way. So I'm happy for you to keep going, or if anyone else wants to jump in.
You can jump in on
By
this.
by all means, keep going. Yes, Kelly?
So I think that you could disconnect the thiophene and make it through
Is there a
Gewald.
first thing, you're a medicinal chemist, so the first
Oh.
compound, so is there something we need to get rid of right away?
Oh, I don't want the piece on the right.
Okay, we got to get rid of that urea, and it's probably
Yeah.
something that they're going to want to make a million analogs of.
Yeah, so back to the, I guess, aminothiophene.
And your favorite way of making urea?
With an isocyanate.
Awesome. Great. So now we've got that compound. Now how are we going to put this together? Is there
Okay.
something hiding in there?
I think there's a hidden nitrile.
Oh, that's too big. Huh. Okay. Yeah, I'll need to practice the highlighting step later. But yeah, there you go. There's your hidden nitrile.
So if you start from the piperidone and the, I guess, I don't know how to abbreviate this, but it's like a nitrile appended to an amide, then you can do Gewald.
Brilliant. See how cool Gewald is? How nice and modular? Fantastic. All right. Well, sometimes the nitrogen is not always next to the heteroatom. We had a question last class where somebody asked that. It's not always there. So in this case, maybe it's a nitration of some sort, a reduction, or maybe there's a nitrile. I don't know. Can someone help us out here?
I can give it a shot.
Okay, let me label some carbons to help you out here. All right, go ahead.
So I guess the first one I would probably disconnect would be, are we so breaking through the thiophene?
That's up to you. You're running the show. Yeah, go ahead.
Okay. I would try to disconnect that amide bond there.
Get rid of that. Okay, let's get rid of that right away. That's certainly, you can do that or you can leave it on, whatever you want. Yeah.
So I would have an aryl ketone from the I think it's the 3 or 2 fluoro, and make that 5 and 4 carbons the carbonyl. Sorry, I'm jumping all over the place a little bit.
And then?
And then from here, could you make that into like a Vilsmeier reagent? And then you have your Fusselman type sulfur with an electron withdrawing group.
So canonical Vilsmeier, just give this, and then adding in to that.
So could you turn that like instead of getting the aldehyde, like keep it at the imine?
You can go even a step further than that. And so what we can do with the Vilsmeier is, as we talked about before, the intermediate before you work it up is that.
Yeah, okay.
This intermediate can be taken without any workup and add an equivalent of hydroxylamine. And then dehydration gives you that, which upon attack with this gives you that directly. How do you like them apples? And all along here was a little rat hiding. Okay. So it's always worthwhile to, it doesn't always work, but if it's next to a heteroatom, it works 99% of the time. If it's just in a random carbon, it doesn't always work. But just conceptually thinking about where the hidden nitrile might be can often lead you to extremely simplified ways of making molecules. So let's take a look at this interesting fungicide called silthiophem. Now, silthiophem is an interesting, I think it's used as an agrochemical, and it's an interesting compound because it has a silyl group in it in the final product. And the discovery route uses a standard type of Gewald, and the Gewald leads to a mixture of something. So, Simona, what is the problem with this?
You can get the thiol either at the bottom position or at the adjacent to the methyl.
Which one do I need?
Bottom. Probably the second one.
Brilliant. Yes, I need that. And so that's the main problem. So after the Gewald happens, I can do a Sandmeyer reaction to give where the NH2 used to be, a bromine in its wake.
Is it easy to control that tautomer?
Nope.
No? Okay.
Not for methyl versus ethyl. That's a challenge. And that's why, but for med chemists, they don't care. Probably they wanted both isomers at the beginning anyway. So, the mixture is fine. And then to finish the synthesis, what they're going to do is treat this with sodium hydroxide. That's going to hydrolyze the ester to the acid. They're going to then do a halogen metal exchange, quench that with TMS, then make the acid chloride, and then finally the amide bond, and they get latitude. Great. Now, the process chemists don't have the luxury of being able to separate things and having even small amounts of impurities. So the way they go about fixing this problem is starting with this compound pure, derived from this ketone, which is apparently cheap and commercial. So by making this through a simple SN2 reaction, they get regiochemically controlled formation of the alpha thiol ketone, which can then be added in a Michael fashion. It will go in not once, but twice, and that will give you, after elimination, just like we saw in Alex's mechanism earlier, will give you this compound with an H here. Notice they don't do Gewald, but rather Feiselman, and they do that because they don't need anything here. The medicinal chemist maybe wanted the bromine there for, ease sake or analogs or whatever, but the process chemist realized that that position, as we learned in lecture number 3, is innately primed for an immediate CH deprotonation. So you can hydrolyze the ester, treat that with LDA, it generates a carboxylate, which is a good directing group. You don't even need the directing group effect, however, and then it deprotonates, and then quenched with TMS chloride, puts it at the only available position to give you that, which after acid chloride formation and amide bond formation gives you the desired product. So the first one was Gewald, stymied by the fact that Gewald had no selectivity with regards to the regio control. And then in order to control things properly, the process chemists pivoted to a Feiselman. Now in the final 15 minutes of the class, we need to talk about probably, I would say, and there's probably a lot of people online that maybe they disagree with me, but I would say it's probably the most useful type of thiophene in drug discovery, and that is the Benzothiophenes. A lot of very interesting medicines based on Benzothiophenes. One of them is shown here called Evista. Now, I need some help in putting this thing together. So what disconnections might we think about? And maybe Nyor, who is so good with the furan, benzofuran, can help us out again with the benzothiophene.
I think one thing that comes to mind right away is the biaryl. Maybe to disconnect that through coupling.
That sounds really good. How are we going to make that?
Actually, okay, so if we sort of follow through what the example that we had before, you can disconnect the 2 and 3 bond and have an ester, sort of like a, I don't know if that's a good idea, but having like a thiocarbonate, if that
Yeah,
makes sense.
it does make sense, but unfortunately, those are not very stable and don't really do the desired. So this type of thing.
No, I'm thinking have an ester at the arrow. So like, sorry, you have like an like a ethoxy or something.
Ethoxy where? Can you give me a carbon number?
So at the arrow, so you have like the thio ester.
Like that?
Yep. And then if you sort of alkylate, then you can install a triflate sort of handle, and then you could do the cross coupling.
Usually, maybe that might work, but not by the mechanism you think. It might be first a formylation and then the sulfur comes back and attacks. So maybe that might work. Okay, yeah, it's certainly reasonable. So you've disconnected the 2,7 bond. We're still gonna have to figure out a way to make this thing. This one is probably straightforward based on what we learned on benzofurans. Going back to your top approach, how do we conceptualize putting that together?
I think maybe you can install the bromo through like a deprotonation quench with like NBS.
Sure. So, NBS by itself is probably enough, but you could deprotonate as well. So we can do an NBS step to get rid of that. Now we've got the corresponding how do we make that?
Can you do like a Frito Crafts type thing there?
Okay. Nobody wants to make a benzothiopene except Noor's idea here.
Well, could you just unpull that strategy that she discussed?
Aha, that's interesting. If we unpull what she just said, it leads us back to the AR here. We do a Frito Crafts then. And so how do we put that together? Can we just use 1,4-dicarbonyl logic and imagine that it comes from something like that upon treatment with acid? Does anybody want to make that? I'm not sure if I want to make that, but you can use an alternative to this.
And what about some kind of gold chemistry? If you have the alkyne and the sulfur and gold one, you do the cyclization?
We'll get to that, maybe, but we want to try to keep it simple. But I'll get to the sort of pi acid in a second. So this type of thing would if you cyclize it, treat it with acid. This is called the Bischler cyclization. The product of this reaction is actually not that, but rather the intermediate undergoes a phenonium shift to actually produce this as your actual product. And then you can do a Friedel-Crafts cyclization. Now, there's yet another way to think conceptually about putting something like this together, which is to imagine starting from an aldehyde, treating that with base and thiodMF. That leads you to this compound. And when you treat this compound with something like methane sulfonic acid, it leads you to this. And this can undergo Friedel-Crafts very easily. And guess what? This compound, you can react it with a Grignard. And it does an addition, elimination of dimethylamine as activated by that electron withdrawing group. Now, let's go back to Debbie's point. Can we think about these things in terms of alkynes? So I'm glad nobody suggested doing a Laroc, because in general, Laroc is going to be stymied by that sulfur. But let's imagine you could find a way to get the alkyne on there. Could you treat it with something? I don't know, indium, gold, silver, a proton, saliva, I don't know. Anything is going to close that ring, okay? You don't need to do anything fancy for a cyclization this trivial. But the challenge is getting this compound without the sulfur muddying up your catalyst. That's the issue. It's probably why it wouldn't be the first thing I would suggest. So Invista was made through this strange reaction called the Bischler cyclization, which in the case of thiophenes undergoes the rearrangement followed by Friedel-Crafts. For analogs, though, this would be certainly a fine way to go.
Phil, could we think about using alkynes, but doing a 1,4 addition on them with the aryl sulfur and still have that halogen ortho to that sulfur present?
Something like this?
Yeah.
And then treating that with some sort of maybe silver or proton or something, perhaps, but then you've got the problem of regiochemistry. You better have an electron withdrawing group here or you're going to get mixtures. It's just not very it's just not very clean.
Well, wouldn't you have on one end
in this particular
the electron, yeah, the electron rich well, the lower aryl, as well as, and then on the top side,
yeah,
you'd have that ketone.
Yes. So you
So
get
that would,
that adduct. You would get that adduct, but then the question is cyclizing it, and I would be reluctant to use palladium with a system like that. I wouldn't recommend it. Maybe we can find a paper that demonstrates that that's possible. But in general, I would avoid using palladium with free thiols or these kind of thiol esters. This is a vanillagous thiol ester, and it's known that palladium reacts really well with thioesters. So don't think of this as a vinyl sulfide. It's not. It's a vanillagous thioester. You know what I mean, Daniel? So I wouldn't want to propose it during a consulting session because I can't be sure. I would. Furthermore, I wouldn't want to do it myself in the hood. And that's, at the end of the day, the ultimate litmus test for is a suggestion worthwhile or not. Would you go to the hood and do it yourself? And this one, I would be really, really worried about vanillagous thioester reacting like this, which is known to undergo lots of palladium chemistry. right? So you're asking for an oxidative addition to happen, insertion to happen at this alkyl aryl halide versus just this carbon sulfur bond. And I can't tell you what's going to happen. I don't know. But these other suggestions, I can guarantee what's going to happen. Let's take a look at this consulting corner question that I think will challenge you quite a bit to think even more differently about how one puts a system like this together. So what's a good disconnection that we can start off with? We've only got 5 minutes remaining. So what's a good disconnection that we could think about? Who's gonna, maybe Sung Han?
Can we cut the arrow bond on C1?
Something like this?
Yeah, I also consider whether can we use radical reactions to coupling the two ring.
Oh, you mean basically a direct arylation. Either way, yeah, okay, let's not get into that, but either way, it's a bromine or a halogen there, right? Okay.
Yeah.
So how do we make that thing?
Or can we do the lithiation on that position?
Maybe I want to remind you of something very annoying about this problem. As I mentioned before, a little trick that medicinal chemists like to use is putting lots of halogen atoms here to make life very miserable. So if we have a bromine here and a bromine here, and you want to do halogen metal exchanges and cross couplings, you cannot bet a kidney that you're going to get the right regiochemical outcome between those two, are you? You're not positive. So that makes it really hard to offer such a suggestion. And furthermore, as is clear from this problem, it's probably going to be something where we want to install that amine at a very late stage. So you're left with this as your only possible logical starting material. Wherein somehow we have to get a Ullmann reaction or something to work there. Now, the corollary to the consulting problem is that trying to do this reaction with palladium or copper leads to no good productive product. And the other problem with this is that even if you tried to do it, remember that the desired amine that you're adding in is a far more reactive amine with itself. So polymerization is going to take over. This is a terrible system to do oxidation insertion into because you've got the electron donating property of the thiophene. Just like indoles and benzofurans, whenever you're trying to do cross couplings to that position, it's always much more difficult. So you've got easy insertion here, difficult there. What do you do? And that gets us to a rare and beautiful form of heterocyclic benzothiopene reactivity. The fact that you can take these compounds and make the thiophene S oxide. Holy cow. The thiophene S oxide. It's not wizardry. You can make this compound. It's a nice crystalline compound. You can run a column on it. And guess what? This one is not at all hassled by the fact that there is a bromine here because we're just going to use base in a simple SNAR reaction. And then you can reduce that off with a variety of different conditions that are halogen sparing. For example, a hydride will do it, and be on your way. This was actually used on a process scale, despite the fact that the process chemists at the time were really worried that that oxidation would be problematic and that the subsequent S oxide would be difficult to reduce, but it was actually used up until I think a phase 1 kilogram scale batch. So very interesting way to take advantage of the innate reactivity of and also a metabolic possible liability of a benzothiopene to activate it for SNAR reactions for analog synthesis and even a process application. Now, in the final 10 seconds or so, we just need a quick Tim, Tiffany, Aaron, Camille, Stone, or Weekly quick radiochemical solution to this problem, and we'll be on our way. That's going to be C14. I'll save you time. The answer has a benzene ring in it. Any of our radiochemists can help us.
Maybe disconnect to the aldehyde and the thiol, or yeah, exactly.
And how about an X here? Or your opposite disconnection would be so we do our labeled DMF for this one. Same thing, labeled DMF. Followed by, this probably needs to be protected. If it was me, I'd prefer the top route because I could start off with something like this. I could easily, with or without the iodine, it doesn't even need to be there. You can just take chlorobenzene, you could take bromobenzene, whatever, you just do the orthometallation, quench with the labeled DMF, and then Feiselman away, but Feiselman in a kind of SNAR aromatic version of Feiselman. Now, in the old days, when we used to go much, much faster and everybody was confused, we would spend the next 30 minutes on biotin, a super important natural product that is found in all your foods and was made commercially for quite a long time. I think there's now a fermentation method to make it, but was made synthetically for quite a long time. And biotin is really great because it gives you an interesting way of thinking about making these saturated thiophene heterocycles from the unsaturated precursors. So this was discussed on YouTube 2 years ago. So you can go back to the 2019 lecture and look at our discussion of this one, as well as the references in the handout. There's a great chem review on making biotin from scratch. So please check that out in your spare time. A lot of really interesting chemistry that we don't have time to talk about today, but we added a bunch of new content today, especially bolstering our discussion of benzofuran and benzothiophenes. So with that, folks, have a wonderful weekend, and we'll see you on Monday for more fun.